So one application of this householder transformation or householder reflection is in the QR factorization. So I'm going to explain what is how do we do QR factorization using householder technique, and then we go back again to this U, and let's see how we can actually find U for this QR factorization. So in the previous video, I talked about the QR factorization using Gram-Schmidt. So Gram-Schmidt is a very intuitive process, but is not robust, right? Now let's see how we do this QR factorization. So again, assume that A is a n by n a matrix. So we let A to be equal to QR. And we are trying to apply sequence of the householder transformation on matrix A to make matrix A to be an upper triangular matrix. Or as I have here in this equation, I will show it by a star, right? Each of these H0, H1, H2, all the way to Hn minus 1, they are householder transformation. And the resulting matrix R is the upper triangular matrix, or the goal is that to make the subdiagonal element of matrix A to be 0. Okay, so each of these H0, for example, this H0 is going to be this I minus 2 UU transpose, right, for the appropriate U. This H1, so this H0 is like, for example, P0. H1 is again this I minus 2 UU transpose for appropriate U. Okay, now let's see what we mean by appropriate U. So at each iteration, as I wrote here, you make the subdiagonal element of matrix A to be 0. So for example, at iteration 0 is step 1, right, to find this H0. What we do here is that, so for example, this is the n by n matrix that I have here. The elements X doesn't mean that all the elements are the same. This is just a convention that people use to represent the elements of a matrix. For the first iteration, we take the first column of A, right? The first column of the matrix A, we take this one, and we make sure that we make the subdiagonal element, meaning that the diagonal element is just A11. And anything besides the first element in the first row and the first column, we want to make it 0 in this column, right? So all this element here, we want to make them 0. Okay, so that's how we find the U. Such a U that after you multiply the X, what is X? X is the first column of A. So I will represent A to be like this, A1, A2, all the way to AN. And we will gonna find a U in such a way that I minus 2 UU transpose times X is gonna be some scalar, let's say constant, C1 times a unit vector, the first unit vector, right? Why is that a constant? Because not necessarily the first element is going to be 1, right? Okay, so that's the first iteration. The second iteration, we do the same thing. Now we take the second column of matrix A, and we make the subdiagonal element to be 0 again. What do I mean by subdiagonal element? So this was the diagonal element for the first column. These two are going to be the elements that are either on the main diagonal or above the main diagonal, right? So the subdiagonal element means this. We're going to make all these elements to be 0. So this one is going to be a step 2, which is going to be H1 times H0 times A. Okay. Remember, I proved that H1, H0, all these they are equal to I minus 2 U transpose. They are orthogonal matrices. They are square, and the transpose times itself. Let's call this one H, for example, for householder. H transpose H is equal to identity, which is the same as P that we find in the previous video. So they are orthogonal matrices. Product of orthogonal matrices is another orthogonal matrix, right? So we're gonna let this H0, H1 all the way to Hn minus 1 to be some sort of so for example, if you have A to be equal to QR, okay, now if you multiply everything by Q transpose from the left side, you get Q transpose A to be equal to R. Remember, Q transpose Q is identity, right? So we make all this, the product H0, H1, H2 all the way to Hn minus 1 to be Q transpose. Okay, so that's how we find the QR decomposition using the householder transformation. So eventually we obtain the upper triangular matrix, or another way to say that we make the subdiagonal elements all to be equal to 0. Now I go up here. Now I'm going to talk about how to find the u. Now that we know what is the application that we have, this is the QR factorization, and now that we know how to achieve this, let's see how to find u. Remember, this p was the same as h, right? So p times x, when you multiply this reflection matrix, this transformation matrix by x, I want to get what? I want to get this x 0, 0, 0. So that all the sub-diagonal elements for the first column should be 0, right? So why did I write norm of x times E1? Why did I write that? How did I come up with norm of x? So I've seen this in a lot of places in the internet, but people don't explain how you get this norm of x. So let's see why we get this norm of x. You see, the first column is x. X is the first column of matrix A, right? So this is x1, x2, all the way, let's say, to xn or xn. A is n by n. This is the first column only. So remember I talked about linear transformation in previous videos. We had a video about linear transformation. And I talked about the orthogonal matrices as well. I said, if you are transforming a vector by orthogonal matrix, we have a couple of properties for that. One, I wrote it down here for you guys. You can see that. You can also go to the previous video and watch that again if you haven't watched it before. Norm of a vector stays the same, meaning that if y is equal to ax and A is an orthogonal matrix, then norm of y is equal to norm of x. Okay, the P is an orthogonal matrix. We proved that. Now, if I multiply that by x, the norm should stay the same. Wait, I'm zeroing out all these elements, but still a norm should be the same. So the resulting vector is going to be something like that, the C1 and then 0, 0, 0. But the norm of these two quantities should be the same. What is the norm of this column? It's going to be what? Norm of x. So C1 should be norm of x. And that's how we find this element. And that's why I have norm of x times E1. E1 is nothing but the first unit vector. Now let's see how we can solve this equation. Okay, so I'm going to go ahead and simplify this a little bit. Instead of P, I'm going to write I minus 2 UU transpose. This is 2, right, times X, right? So let's just expand this. I multiply X by I get X. 2 UU transpose times X, I get what? So this U transpose X, I write it as a U dot X, as a dot product, times U. You might say that how I did this. Let me just do it in a slow motion. So U transpose X. What I can do, I can first group these two together. I can get U transpose X. But wait, U transpose X is just a scalar, right? 4 times U is a vector. Doesn't matter if you multiply 4 times U or U times 4. So I can move this U to this side. I can write the U transpose X times U, right? And then I let U transpose X becomes U dot X, the dot product of U and X, okay? So for simplicity, since I know that U dot X is a scalar product, so I let it to be alpha, right? I let U dot X to be alpha. Alpha is a scalar, okay? So what I get is that X minus 2 alpha times U. Okay, very good. Now, this X minus 2 alpha times U is a vector, right? Because X is a vector and U also is a vector. So X minus a scalar times U. I want the first component of that to be is equal to norm of X and all other components to be equal to 0. Okay, very good. So let's do this one. Let's do it. So I'm gonna have x1, the first component of x, minus 2 alpha u1 equal to norm of x. Why do I that? Why is that? Because of this, right? And all other elements, let's say we have n elements, to be equal to 0. Why is that? This. Okay, good. So let's solve this equation. So I want to find u's. My goal is to find u's. Okay, you have to be clear on that. So u1 is equal to x1 minus norm of x divided by 2 alpha. And ui is equal to xi over 2 alpha. So U1, I get it from this equation 1, and UI, I get it from equation 2. Okay, so according to 1, according to 2. But we know something else as well. We know that U has a unit norm. That's how we define U. U was a vector with a unit norm that was perpendicular to the hyperplane G, right? The hyperplane was the hyperplane that was acting as a mirror for this vector X. Okay, very good. So now let's see what we can do. I'm gonna go ahead and square U1, right? And also square UI, each UI, I from 1 to n, and then add them up together. That's what I'm going to do. So U1 square is nothing but x1 minus norm of x square divided by 4 alpha square, right? And UI square is nothing but xi square divided by 4 alpha square. Now let's add them up together. You might say why? Why we are doing this? Remember, U has a unit norm. If I add them up, what do I get? U1 square plus U2 square plus U3 square all the way to UN square. This is nothing but norm of U square. So I know I get 1. Okay, so that's why I'm doing that. This is here norm of U square. It's gonna be equation 1 plus equation 2, and they have the common denominator 4 alpha square. This one is 1, right? So this is gonna be 4 alpha square equal to x1 plus norm of x square minus 2x1 norm of x plus sigma I from 2 to n. Remember, xi square. Because for I1 we get this x1 square, right? So I from 2 to n. Where is this coming from? Where is this coming from? This is coming from here. So this is I here changing from 2 to n, right? Because I1 is for here. I1 is here. For I1, we had a different equation. Remember, for I1, we set it to be equal to this. For all other I, we set it equal to 0. Okay, very good. Now let's take a look at that. I have a sigma I2 to n xi square. I can add it to this x1 square. I get what? If I add this and this, I get nothing but norm of x square. X1 square plus x2 square plus x3 square all the way to xn square. It's nothing but Euclidean norm of x square. And that's what I have. Euclidean norm of x square for this one, another Euclidean norm of x square from this, and then minus 2x1 norm of x. 4 alpha x square is equal to this. I go ahead and take a square root from both sides. I get 2 alpha equal to this. Okay, but now wait, do I need to divide it by 2 to get alpha? Not really. Why is that? Because I need u. I don't care about alpha. But here in the denominators, I have 2 alpha. So I leave it at 2 alpha. Okay, very good. Therefore, u1 is going to be x1 minus norm of x divided by 2 alpha. How do I know that? Based on this equation. u1 is x1 minus norm of x divided by 2 alpha. And ui is equal to xi divided by 2 alpha. So if you write it in a vector format, as an element-wise vector format, you get u equal to this. This is the first element that we had here. This is u1. This is u2 all the way to un. And this is how you find the u for the QR factorization. So if you find this u, and using this u, find p, or let's say h naught, right? Using equal to I minus 2 u transpose, and you multiply by x. The x, which is the first column of matrix A, and this is the same x as here. So this x is going to be x1, x2, all the way to xn, and this is going to be this. Or xm, depends on the dimension, right? So this is going to make all the subdiagonal element to be 0. And you do this process for a second column, for a third column, until you get all the subdiagonal elements of matrix A to be 0. Okay, so thank you so much for listening, guys. This is what I had for the QR factorization using householder transformation. See you all in the next video. Thank you.